Good day. This is a short video on flow networks and maximum bipartite matching. Specifically, we will look at a solution of the exercise from CLRS textbook 26.3-3. It's a nice exercise to explore how flow networks can be used to model maximum bipartite matching problem and how the Fulkerson method works to find maximum flow. So what is a bipartite graph? It's just a graph where the set of vertices is divided into two non-intersecting subsets, L and R, such that all the edges go only from the vertices in L to vertices in R. It's an undirected graph. So there are no edges between vertices in L, and there are no edges between vertices in R, just edges going from vertices in L to vertices in R. So for example, here is an example of a bipartite graph. We have a L set of vertices and we have an R set of vertices. And then a matching is just a subset of edges, such that for any two edges in the matching, they do not share any endpoints. So for example, this edge and this edge is a matching. They are two edges, they do not share endpoints. And we're looking for a maximum matching, that is the matching with the maximum possible cardinality, maximum possible amount of edges in it. So it seems that here it's easy to construct a matching of size 4, for example, taking this edge, this edge, this edge, and this edge, or this edge, and this edge. So how do we model this as a flow problem? What we do is we create two vertices, a source vertex and a sink vertex. So let's have a source vertex and let's have a sink vertex. Then we make the graph directed, because that's what flow networks are. They are directed graphs. So we create the direction for these edges so that all edges go from vertex in L to vertex in R. And then we add edges that connect the source to all the vertices in L. And we add edges that connect all the vertices in R to T. So that's the graph that we get. Now the exercise asks to give a good upper bound for the length of the augmenting path in any fourth Fulkerson algorithm running on this kind of flow network. So to do that, let's first draw here a graph that will be our residual network, and we will modify that graph as we send flow. In addition, we say that the capacities of all the edges here are 1. But we do not show that in the picture here. We assume that all the capacities here are 1. Okay, so now we have a residual network, which is initially just the original flow network. So let's send some flow along some augmenting path, and here we have augmenting paths going from S to T, all of which has length 3 edges. This could be something like this, or this could be something like this, or something like this. Any of those could be chosen by a Ford-Fulkerson algorithm or the Edmonds-Karp implementation of it. So let's say we send 1 unit of flow here. Then the residual network will be modified to show that we have a possibility of sending the flow back, but we cannot send any more flow through these edges because all of them have capacity of 1. So we now have this kind of residual network. The next iteration of a Ford-Fulkerson algorithm would again send flow along some augmenting path. And what kind of paths we have? We have still these paths of length 3. We have also one more path that we could send flow that is different from the other paths of length 3. We have, for example, this path that we could send flow. But the Edmonds-Karp implementation of Ford-Fulkerson would choose a path with the shortest length in terms of edges. So let's choose one of the paths of length 3. So let's send flow through, for example, this path here. So we send flow through this path, flow of 1 unit, and that means that the residual network gets modified to show that we can no longer send any flow in this direction, but we could send it back if we want. Again, the next iteration of Edmonds-Karp algorithm would choose the shortest augmenting path, which has a length of 3. So this could, for example, be this path. Okay, so let's send 1 unit of flow on that path. So we get this kind of residual network. Finally, the next iteration of the Ford-Fulkerson method would find only one possible augmenting path in the residual network. So if you look carefully, the only possible path from S to T in the residual network goes like this. Here, 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 and here. There are no shorter paths. So any Ford-Fulkerson method will have to choose this as the augmenting path. And let's see what happens when we send flow along that path. So that is the path where we send 1 unit of flow. And that is actually the path that demonstrates the longest possible augmenting path in this kind of problem. So this path, as we can see, has, if we generalize this to a larger example with V vertices, we can see that the length of the path in terms of number of edges is V plus 1, where V is the number of vertices in L plus the number of vertices in R. So here we demonstrated this upper bound that the exercise asks to demonstrate, a good upper bound. What happens when we send flow along this path? We see that the flow, 1 unit of flow is sent here, then it's sent backward here, so this means that it cancels this flow. Then it goes here, then it cancels this flow. So we change our mind, the algorithm changes its mind, then it goes here, then it goes here and cancels this flow, because it goes in the opposite direction, and then finally it goes here and goes here. So here is the final flow of magnitude 4 that we construct. And this corresponds to this matching of size 4, maximum matching in this setting. What this example demonstrates is that the length of the augmenting paths in Edmonds Karp algorithm increases. So these paths are shortest paths in terms of the number of edges, but as the algorithm goes, these paths become longer and longer and longer. And here we constructed an example where the path actually includes all the vertices in the graph.